No, you need to be standing at the keyboard, right?
Good afternoon. My name is Ronald Porterar. This is Sean DiPascal and Matthew Cosa. We are the Mighty Mech Panthers, and our project is the NASA Lunar Robotics project. The purpose of our project is to design and build a mining robot that can traverse the lunar soil while keeping a weight limit of 80 kilograms and staying within our design specifications.
Some of the design considerations that we had were the movement of the rover, what type of mobility we wanted to use, whether it be wheels, treads, legs, or a hybrid combination. What collection mechanism we wanted to use, whether it be a single scoop or a continuously operating conveyor belt, and what dumping mechanism we wanted to use to deposit the collected lunar regolith into the collection bin. And finally, what control systems we wanted to use, what sensors and cameras, if any, and how they adhere to the data transmission limitations.
For our mobility system, some of the things we considered was wheels. It would be the cheapest and easiest to implement, but give us the least traction. After that, we considered adding links to the wheels to add some traction. This would be heavier than the wheels, but and then afterwards, we decided to go with our final decision with the track system, which is going to be the costliest, but it would give us the most traction.
For the collection mechanism, we had two choices, the conveyor belt system and the scoop system. The conveyor belt system has the advantage of the continuous pickup, while the disadvantage is a higher cost and also higher complexity. The scoop system, the advantage of it is that it's simple and low cost, and the disadvantage is that it has a limited capacity and it requires more power to drive.
Some of the design changes that we made from our initial design to our current design are the frame length. We shortened the frame by roughly 12 inches. We've switched the frame material from 16th inch wall to 8th inch wall, 60-61 2x1 box aluminum. That is to save cost as well as implement a higher factor of safety. We added a support frame for the collection bin, as well as placed the collection mechanism outside of the footprint of the rover. And finally, we switched to a gear-driven output shaft to a sprocket-driven output shaft. On top of that, we also went from individually sealed, self-contained gearbox units to open gearbox units, so that way all of the electronics, including the motors and gearboxes, will share a single housing. And this is to make servicing the rover easier in case any mechanical failures occur.
To run analysis on the base of our frame, we used SolidWorks. We used the Von Mises stress criteria and applied a load of 1200 newtons. It's roughly 120 kilograms was our goal, and we got a safety factor of 9.9.
NASA uses this competition to gather information from 50 teams across the world. The lunar regolith can be used for the production of energy, and this sets up the groundwork for future colonization missions that NASA may implement. As well, our team consists of 3 mechanical engineers, 3 electrical engineers, and 2 computer engineers, and we are a multidisciplinary team.
This is some of the estimated budget. It shows the prices of some of the individual components that we've purchased or plan to purchase, and altogether they add up to a final cost of roughly $5,000. Questions?
I didn't see a schedule.
No, we didn't put a time limit on this presentation.
Oh, you should.
We will.
Okay.
Yes.
Oh, so this is for a competition, right?
Yes.
Do you have the specification? I might have missed it. Do you have the specifications for the competition?
There are a number of specifications for the
Okay.
competition.
Can you give just a general, quick overview at some point, just so that way we know what you're doing?
Well, in one of the first slides, you mentioned.
Okay, all right,
Yeah,
sure. Sorry, I might have. That's what I might have missed that. Sorry. Okay, so you're just lifting regolith and putting it one side to the other.
Yeah, we also
Yeah,
plan
it's
to do an autonomous function, but that will be handled by the electrical team.
Oh, okay.
And we have a weight limit of 80 kilograms, and we have also a length of 1.5 meters by what? 0.75 meters by 0.75 meters.
Okay.
And those are our design limitations. We also have a kilobyte limit of 50 kilobytes per second. And
It may be worthwhile spelling those out. Certainly the autonomous piece that you just mentioned, have that in somewhere in your opening, one of your opening frames.
We didn't include it because that's more like the electrical side. so-
No, but say that.
Okay.
Yeah, we understand you're mechanical, so.
Perfect.
And you have finished your presentation 1 minute 15 seconds earlier, so you need more slides.
Yeah.
I mean, citation for your graphics are missing. I couldn't see any citation on your graphics. And the GL component is kind of missing. You need to mention about it more.
Which column was that? What's the last statement?
Global learning.
Global learning component.
They have global there.
Yeah, but I
We
think
originally had 3 slides individually of the 3 single global learning components, but we felt that they kind of ran over each other.
Okay.
So we combined them to kind of
And
keep
you-
it short and sweet.
okay. You need to also put your timeline.
Yeah.
A couple more questions about design. Is there going to be any sort of obstacle or anything like that? I noticed you all, it's a little bit tough to see with the scale, but are there going to be rocks or anything? I know the ground clearance is pretty low.
Yeah, well, there are going to be rocks as well as
Okay.
craters in the surface.
Okay. So you have to go up and down?
Yeah, that's
Yeah,
part of the
unless you can avoid them.
Okay. Oh, you can avoid them?
Yeah,
Okay,
yeah.
so you're driving, but you're driving, but there's also an autonomous component?
That is a choice.
Okay,
You could-
okay,
The autonomous would ideally
Sure.
sense those.
right, okay. Oh, nice.
Also, the craters are going to be 3 centimeters in depth.
Oh,
So they're-
You have some definition of the craters already?
yeah, exactly. So sand will be a little bit higher.
So
Anyway,
they're not going to be that deep.
yeah, okay. And what about the rocks? Are there any sort of, I know you said there may be
There's going to be rocks,
obstacles.
but NASA is not trying to have them there purposely. It's just
So you
a
happen to
result.
be. So the one, I think 2 years ago or something, this group, the same people who did this, their big problem was whatever motion they used, they had some sort of track or something, but it kicked up a bunch of the regolith. So this was all inside of a big, I don't know, bubble, whatever they want to call it. And so they couldn't even see their rover once it started moving because they kicked up all the regolith.
That wasn't
Yeah.
actually their
Okay.
mobility. That was their collection mechanism. They used to
Oh,
store
okay,
it.
all right,
Yeah,
yeah.
they actually have outlawed what they did because it picked up so much dust.
Okay, all right. Anyway, I don't know if you guys have seen that.
What makes, like, who wins? What do you, like, if everyone kind of accomplishes the task, then, like, does everyone win?
There's a point system, and for every task you complete or don't complete, you get points either added or deducted. Just by getting into competition and passing the safety inspections, you start off with 1,000 points. And then for the weight, they start deducting points on each kilogram. You can't go over 80, but for each kilogram of weight, they deduct a certain amount. And it's just like that. And you have to collect at least 10 kilograms. Yeah, for your run to be valid.
Are you, like, timed on it? Or
Yeah,
is
10
it-
10-minute run.
Yeah.
No, what I'm saying, within the 10 minutes, let's say somebody did it faster than you, or you did it
No,
faster than
you,
them, do you win
you
based
do
on?
as much as you want within the 10 minutes. You can go back and forth.
Gotcha,
Also,
The more soil you collect, the more points you receive.
okay.
Also, with the autonomous function, we have a way of winning because it's 500 points. So if we just collect the minimum amount of soil, which is 10 kilograms, we could potentially win because no team has completed autonomous function before, successfully.
Is the autonomous functionality going to be driven by some kind of camera?
Yes, it's going to use a CMU cam.
Okay.
We plan to purchase that in January since it's not available at the moment. So we don't have a lot of information about it.
But at least try to address that in one of your frames. Because if you've got a driver, you don't need a camera, but if you're going autonomous, you will need a camera.
We will also have a driver because if the autonomous function fails, we need to have a backup plan to keep functioning while the competition is running. For example, if our robot fails during the competition, like if it stops the autonomous function, we could take control of it manually and continue the competition.
Well, say that. Yeah, say that.
There are also levels of autonomy. You don't have to do the whole thing autonomous. The 500 points you mentioned was if you do the 10 minutes autonomously, but you can do from one side to the other and get a certain amount of points. Yeah.
So then say it's going to be a hybrid. describe it. Does that make sense?
Yes.
Do you have any other questions?
One more quick question.
Yeah.
So you have what, $5,700 to raise, right? I know you have a bunch of people, but how do you all feel about that dollar figure? And
It's
typically
high.
these sort of things, that's what derails the whole project.
Right, that's a bit high. We're also hoping to get some funding from the Florida Space Grant Consortium. They don't have anything left for this calendar year, but in January they'll be able to provide us with some funding.
Mhm.
And we're also doing some independent fundraising to try and bolster that amount.
Okay, just be aware.
Very good.
Okay, then thank you very much.